Let us now discuss the spectral series of hydrogen atom. We already studied in previous section of hydrogen spectrum that whenever an electron de-excite in a hydrogen atom corresponding to each de-excitation pair of energy levels, a spectral line is plotted in the spectrum. Now, if we talk about all the spectral lines in the hydrogen atom, we can state in hydrogen spectrum, each group of spectral lines corresponding to electron transition to a particular state. Here we are talking about all the electron transitions which are de-exciting from any higher energy level to a particular state. These are called, here we are talking about each group of spectral lines. The group of spectral lines are called spectral series, and these are divided in 6 categories. And these categories will discuss with the help of energy level diagram of hydrogen atom. Let's have a look on this picture. In this diagram, you can see all possible transitions of de-excitation for an electron to any higher energy level to lower energy level are shown. Here, for the sake of clarity, the difference between the energy levels are not shown according to the values of their energies. But here we can see from any higher orbit to n equals to 1 orbit, when the electron transition takes place, all these energy values forms a group of spectral lines, because here we can see that the first line, second line or third line may have some differences, but then onward the lines will be almost of similar energies, because after 4th or 5th energy level, the energy level gets very close to each other. So in this situation here we can see that first 2-3 lines will be distinguished, then onward we can see the lines are very close to each other. And this group of spectral lines which are corresponding to transition to n equals to 1 is given a separate name as Lyman series, which is one of the spectral series among many. And similar to this, one electron makes de-excitation to n equals to 2 level from any higher orbit. This group of spectral series is again given a separate name called Balmer series. Similarly, one electron makes a transition to 3rd energy level, again the group is given a name called Paschen series. And for n equals to 4th transition, the spectral series is given a name Brackett series. And for n equals to 5 transition, it is called Fund series. Basically, in a practical situation, these 5 spectral series are observed, but in some specific laboratory conditions, when electron makes a transition to 6th level, this series is also sometimes practically observed. Is given a name Humphrey series. So these are the 6 discovered spectral series in hydrogen spectrum. Here Lyman series is the one of which the energy levels, difference energies which are emitted while de-excitation of electron. These energies are of the range of ultraviolet energy. So Lyman series is found to be in ultraviolet region of the spectrum. Similarly, when Balmer series is obtained, it is a part of a visible region. Or we can say whenever a photon is emitted by de-excitation of electron from any higher level to n equals to 2 level, the photon energy will be in the visible region and the light emitted can also be seen. And then onward partition series energy levels differences of which the photons are emitted during the excitation of electron. These are in infrared region. And you can say after partition series all these are in the range of infrared region. And these spectral series are almost overlapping with each other. Like if this is the first line of Lyman series, this will be the last line of Lyman series, which is corresponding to the transition of electron from infinite energy level to n equals to 1. And these differences are quite distinguished from first line of Balmer series and last line of Balmer series. As you can recall in previous section, we have seen that a few initial spectral series are separated from each other. Even partition series, we can say its first line and its last line will be significantly different from Balmer series, but then onward for bracket series, when we'll calculate the energy of first line of bracket series, it is even less than the last line of partition series. So this will overlap with the partition series. Similarly, last line of bracket will overlap with the first line or initial few line of front series and so on. So in this situation, we can see that initially three series are separated from each other. Then onward the series have overlapping in the infrared region. Let's discuss about the first and last line of different spectral series separately also. Let's continue our discussion on different spectral series and their series limit. We have just now studied that Lyman series is obtained whenever electron transit from any higher orbit n2 to n1 is equals to 1. And in this situation, if we talk about the first line of the Lyman series, this will be corresponding to the transition from 2 to 1. And if we talk about the last line of the Lyman series, which is also called a series limit of the Lyman series, this will be corresponding to infinity to 1. And all these lines in between first and last line of the Lyman series have their wavelength which is in the range of ultraviolet region. The wavelength you can easily calculate by using Rydberg's formula we have already discussed. Now similar to this, if we talk about Balmer series, this is corresponding to higher orbit n2 to transition to n1 is equals to 2. Here if we talk about the first line of Balmer series, this is corresponding to transition from 3 to 2. And the last line of Balmer series is corresponding to transition from infinity to 2. And all these wavelengths between first and last line are corresponding the excitation of electron, the photon emitted wavelength. This lie in the visible region, and most of these lines are close to red and orange radiation of visible region. That's why one hydrogen spectrum is obtained. During discharge of hydrogen gas, some pinkish reddish light is seen, which is corresponding to the transition of Balmer series. If we talk about partition series, it is corresponding to the transition from any higher orbit to n1 is equals to 3. And here first line is corresponding to transition from 4 to 3. And last line is corresponding to transition from infinity to 3. And here the wavelength lies in early infrared region, which is not overlapping with the visible region, but its last line overlaps with initial few lines of bracket series, where from any higher orbit n2 to n1 is equals to 4 transition can be considered. And here first line is corresponding to transition 5 to 4, and last line is corresponding to transition from infinity to 4. Here the wavelength is again in infrared region, or here we can see the region becomes deep infrared, whereas in partition series it is early infrared. And in front series, any higher orbit n2 to n1 equals to 5, transition takes place where first line is corresponding to the transition from 6 to 5, and your last line is corresponding to transition from infinity to 5. Here also the wavelength lies in infrared region. And last for Humphrey series, we can say the transition is from N2 to N1 is equals to 6. This is rarely obtained in general, but practically in laboratory experiments it can be obtained, where first line is corresponding to transition 7 to 6 and last line here is corresponding to transition from infinity to 6. Here also lambda lies somewhat in infrared region, or some in, we can simply state as energy difference decreases, wavelength increases. This will be a long wavelength range where the series lies. And you must keep all these series limits in your mind, because various questions based on these series limits are also asked, where you need to use the whole information.